So, yeah, so this part of the course we will be looking at dimensionality reduction techniques. Dimensionality reduction. Yeah. So, what is the dimensionality reduction problem? Yeah. So, yeah, so the video is started. Yeah. Okay. Yeah. So, what is the dimensionality reduction problem? Yeah. So, I will just give you a quick example. Okay, what this problem is. Okay, I have to be careful. Yeah. So, let me just show you something. Yeah. Okay. Yeah. Okay. So, let us say this is some plot of a galaxy. Okay, this is galaxy and there are stars, and typically I mean this galaxy is its spiral. For whatever reason it is spiral. Okay, what that means is the galaxy somewhat looks like this. Okay, I mean in 3D it somewhat looks like this. Yeah, that means there are no stars in all directions. Yeah, I mean stars are more or less along a plane. Yes, somehow the stars are more. The reason for it is very, I guess it's a very deep physics. I don't understand it, but yeah, it's fascinating actually why stars form galaxies only this way. I mean, there are spherically symmetric galaxies also, but lot of galaxies are this spiral. Yeah, most of the stars are along that one plane, and yeah, Milky Way is spiral, and that's why you see like the name Milky Way is derived by it forms a band across the sky, right? Yeah, because we are looking at the galaxy from one side. So, if we look we are looking at the galaxy like this. So, you see this band of stars along one direction. Yeah, but actually if you look at from the other direction it looks like this. Okay. Yeah. So, yeah, so let us say you have the coordinates 3D coordinates of all these stars, right. You have the 3D coordinates of all these stars. So, you have x, y, z for every star, and yeah, and if you plot it, it might look like this. Yeah. So, so the thing is I have plotted it with some x, y coordinate. Yeah, let us say that x, y origin is somewhere this corner or something. Yeah, and we have plotted it like this. Yeah. But yeah, it is very nice to plot it like this, but this is not the natural axis to plot. Yeah, this is not the natural axis to plot the galaxy, right.
So, what do you mean by natural axis?
Yeah, what do you mean by natural axis, right. Now, if you look at the galaxy, yeah, I mean how does the galaxy look, right. I mean most of the stars, yeah, in that it is mostly along, it is not really a 3-dimensional object in some sense. Yeah, it is all the stars looks kind of lies in a plane, close to a plane, right. Most of the stars lies close to a plane. Yeah. So, maybe I should put my x and y axis. So, I will put one x axis, let us say like this, yeah, a y axis perpendicular to the plane, and a c axis like this. That is a more natural coordinate system for the galaxy, right. I mean yeah, yeah. So, that is very so what is it, what way it is natural, right.
By concentration.
Yeah.
We are able to see like all the objects, more or less all the objects, but when we see it through this, like through this view, most of them would be like clustered at a point.
No, changing the changing the x with the coordinate system does not mean the shape of the plot is going to change. It will just the axis will be there, we will be looking at
no, like if we have axis in the plane itself, like the plane they are following, then we can see the spread and
here also we can see the spread and everything.
No, but if we take like the earlier view, so then at a point there would be multiple of them lined through the other axis.
Yeah, so that is yeah. So, I will give you another more interesting reason, yeah, which is, so let us say right now I am plotting this, I am taking this matrix of x, y, z coordinates, right. So, you will get some big matrix, actually I can actually print it out, this is some code running, okay. it is a big matrix and all the values will be kind of large. Okay. There will be x values ranging from some very big number to very big number, y values ranging from very big number to c values also very big number to very big number. Yeah, this matrix is actually all the numbers are roughly very large values. Yeah. What if I put the coordinate system as we just talked about, that is so the origin is somewhere in the middle, x is let us say along that direction, y is along the perpendicular direction, c is in this direction like this. So, now how will the matrix look like? The values along C will be, it is actually not completely 0, it is not exactly on the plane, it is slightly off from the plane here. The values C values will be minute values. It might be in a specific range, but it will be say maybe it is between plus 10 or minus 10 or something, do not take large values. So, earlier you have x y z coordinates, all of them were taking arbitrary large values and everything, but now you have, if you change that this thing, only the x y coordinates are really important. The c coordinate, it is only taking small values. If the galaxy is perfectly planar, for example, the c coordinate will be 0 as is that. So, yes, that is I mean that representation, the c coordinate is we are kind of making the c coordinate less important, and that is the essence of dimensionality reduction. So, typically you have lot of points in high dimensional space. In this case it is actually 3 dimensional space, we can visualize it, but typically when you work in machine learning or algorithms or anything, the input data points are going to be very high dimensional, it is not going to be 3, it might be 1000 dimension, million dimension and everything, and then you will not be able to visualize like this and actually draw the x axis, y axis, z axis or something like that. So, then we need to find a coordinate system for this data, such that let us say we would ideally like to have a ordering of these coordinates x, y, z, such that x is the most important axis, the maximum variation happen along x, the variations. The next maximum is y, the next maximum is c, and maybe after a while, let us say it is a 100 dimensional vector, maybe after 5 dimensions most of the variations are going to be very less. So, then we can actually convert that 100 dimensional vector to a 5 dimensional vector, then we can ignore the later coordinates because maybe it is very minute values, and that is what dimensionality reduction is. So, typically your raw data that you get, whichever application you are working, whether it is data science, machine learning or algorithms or anything, the input data points will be very very high dimensional, but typically the data will lie very close to a small dimensional subspace, and the question is how do we find the subspace? Once we find this subspace, we will just put our coordinate system into that subspace and we will just have the points in that subspace. So, instead of working with this 100 dimensional vector, we will be working with that 5 dimensional vector and we will be saving all the processing time we will be saving, and that is what dimensionality reduction is. So, so I will show the later part of the code, just a second. So, our goal is to find this this axis system. So, there is a red, green, black axis. So, the goal is, so you are given this matrix, the number of rows is the number of data points and there are 3 columns. From that we want to find the red and the green axis. The red axis has the maximum variation in the data, green axis has the next maximum, and this again these are orthogonal axes, 90 degrees, and everything. Okay. So, this is our goal, we want to find so the algorithm for finding this, there is a very nice algorithm for finding this, which uses nice amount of linear algebra and everything, and the thing is we can, it is guaranteed to find the best x and y axis. There is a theoretical proof which tells you that the output of this algorithm is the best x and y axis, I mean that fits the data.
That means it captures like with all of the data like in minimum.
Yes, yeah. And that proof also we will see. That is the plan for the next 4-5 lectures. Yeah. So, yeah, so for understanding this, first we need to little bit revise our linear algebra. Okay. We need to little bit revise our linear algebra. So, yeah, so today we will just get used to, I assume you have done linear algebra once before, yeah, but we will just revise those terms once again quickly in this class, yeah, and we will see how to use those things to get this subspace. Any questions about what we are trying to do? Yeah. So, I will see one more application. This is a like a toy example that I came up with. Yeah, I will show you a very particular example. Yeah. So, this is possibly actually used. Yeah. So, let us say you have your camera and you are taking a burst picture. A burst picture meaning they take lot of pictures in like a few seconds, right, and you will get something like this, yeah, images like this. Now, yeah, you can store that set of pictures just like that. Yeah, let us say this is 100 by 100 pixels each image, yeah, and let us say it is also a RGB image. Yeah. So, one image is how many, what dimensional vector?
Number of pixels into 3.
Yeah. How much is the number of pixels? 100 into 100. Yeah. 100 height, 100 width. Yeah.
It is given, it is 100.
Yeah, let us say I am assuming 100 by 100. Yeah. Typically, it will be much more than 100 by 100. I am just saying some reasonable number. So, it is going to be 3 into 10 raised to 4 integers. Yeah. If it is a 8-bit integer, you store it. It itself, one image itself is a large size, large dimensional vector. Yeah. And you have all these vectors to store. Yeah. But so this is a very bad way of storing. It is not like all these images are completely independent of each other, right. Most of these images have the same structure, only minor variations are there. Yeah. So, in the galaxy case we have only 3 dimensional vectors. Here it is 3 into 10 raised to 4 dimensional vectors. Yeah. Question is, okay, instead of storing this 3 into 10 raised to 4 dimensions, yeah, can we store some maybe 100 or even 1000 dimensions? Just store some 1000 important dimensions that is common in all these pictures. Yeah. And without yeah, so so I think they have applied these algorithms. This is actually what happens when you do 4 components. That means I actually find the best 4 dimensions. Yeah. And 4 dimensions itself is actually gives quite good images. Instead of 4 and 3 into 10 raised to 4 dimensions, for each of these images only 4 dimensions are stored, and it is still good to give reasonable clarity pictures. Yeah. So, it is a very important technique, yeah, which is heavily used in machine learning, data science, algorithms, yeah, and we want to understand this. Yeah. This yeah, I am using a slide by somebody elsewhere. I will give the reference. Yeah. And yeah, he has actually run this algorithm and put it there. Yeah. Okay, let us revise some yeah, linear algebra concepts first. Yeah. So, everybody knows what a vector space is. Yeah. So, what is a vector space?
The combination of vectors which span a space, that is the vector space.
A vector space is a set of things, a set of objects. Yeah. It should satisfy certain properties. So, what are the properties it should satisfy?
The combination itself lies inside that space that is spanned by all those vectors.
Yeah.
Is a field under addition and multiplication.
Yeah. So, for defining a vector space, first thing you need is a field. Okay. So, you can only say that the V is a F vector space. Yeah. So, whenever you say some set is a vector space, it is with respect to some field. It might be the real field. So, what is a field? I will not go into what field is. Yeah, it is there is a addition operation defined and a multiplication operation defined, and all of this has inverses and everything. Yeah, there is additive identity 0, there is a multiplicative identity 1. Yeah, all those things are there. So, rational numbers are a field, but integers are not a field. Yeah, because there is no multiplicative inverse. I cannot do 1 by 2, 1 by 3 or anything like that. Yeah. So, rational numbers are a field, real numbers are a field, complex numbers are a field. Yeah. And so, all of these are infinite sets. Okay. I mean rational, but there are fields which are also finite, which is yeah, countable only. So, can you give example of a field which is finite? So, Q is the rational number, C is the complex number, these are all infinite fields. So, what is a field that is finite? Yeah, modulo 2 is a field.
So addition is there.
Addition is there, multiplication is there, yeah, additive inverse is 0, multiplicative inverse is 1, and those are the only two elements. Yeah, very simple, easy field.
Modulo 1.
Modulo 1, then yeah. Yeah. So, I mean you can do modulo any prime. Yeah. So, f p, yeah, is the number 0 to p minus 1, 0 to p minus 1, and you can do addition and multiplication modulo p. Yeah, addition modulo p, multiplication modulo p. Yeah. And yeah, so yeah, if you remember your number theory, yeah, it happens that for every prime p, yeah, if you do addition modulo p and multiplication, if you define your addition as addition modulo p and define your multiplication as multiplication modulo p, yeah, then this becomes a field for every prime. Yeah, and if p is not a prime, it is not a field. Yeah, there will not be I mean it will there will be additive inverses. Yeah, you can always find additive inverses, but multiplicative inverses will not be there if its p is not prime. Yeah, so p has to be prime. Yeah, so there are finite fields also. So this is called a finite field. Yeah, and there is common infinite fields which are you are more familiar with. Yeah, and both of these are important. Okay, finite fields are heavily used in coding theory and everything. Yeah, all your error correcting codes are or that entire theory is based on this theory of finite fields. Okay. Yeah. Okay. So, now we understand what a field is. Yeah. Now, a vector space, yeah, is a set. Yeah. We will say V is a F vector space. Yeah. So, for defining a vector space, so there should be a way of multiplying elements in the field with vectors in the set V. Yeah. So, the elements of the field are called scalars. Yeah, these are called scalars. Yeah. The elements of the set V will be called vectors. Yeah, V can be any set. Yeah. So, V is a F vector space. For doing that, we need to have a definition of multiplication of a scalar quantity with a vector. Yeah. So, there is normal real vectors, you know how to multiply by a scalar, you multiply every coordinate. Yeah. If it is a matrix also, you can multiply by a scalar, you multiply every entry of the matrix. Yeah. Let us say you have a function. Yeah, function from let us say function from 1 to 6 to real numbers. Yeah, I can define I can multiply that function with a real scalar value, you will get another function which again outputs a real number. Yeah. So, there can be all sorts of sets, as long as you have a way of multiplying the vectors with the scalars. Yeah, that is the first thing needed for vector space, you should have a way of multiplying the scalars with the vectors. Yeah.
Necessary like even if we look for like a way that we can multiply scalars with vectors, why
So, the vector space definition requires that. Yeah. So, a vector space is a like a set of vectors where you can take scalar linear combinations. Yeah. You can take let us say alpha beta gamma belongs to the field. Yeah. This field can be any of these things. Yeah. And then you can take alpha times v plus beta times u plus gamma times w. Yeah. This will also belong to the vector space. That is the main thing about a vector space. Yeah. So, you can take a scalar linear combination. So, for taking a scalar linear combination, first I have to define how to multiply a scalar with a vector. Yeah. So, once that is defined, then you can take linear combination of vectors, and any linear combination of vectors should also belong to the vector space. Yeah. Yeah. And so, when you have a field, there is the 0 element, right. There is a element which is the additive identity. Yeah. So, 0 times a vector should be equal to 0. Okay. Yeah. And actually there is a set of 9 or 10 conditions that these operations should satisfy. Yeah. For V being a vector space. Yeah. I will not enumerate all those definitions, yeah, in the class today. Yeah. You can go to a standard reference and refresh your knowledge. Yeah. So, for a vector space there is a addition operation within you can add vectors. Yeah. You can also sometimes multiply vectors, but that is not necessary. For a basic vector space you should be able to only add vectors, and you should be able to multiply with the scalars. These are the only things needed for vector space. You should be able to add vectors and should be able to, yeah, linear combination actually it includes both the operations together. Yeah, scalar multiplication and addition of vectors are there. Yeah. So, for defining a scalar linear combination, I should tell you first how to add vectors, secondly how to multiply with scalars. Yeah. So, you need to define those two conditions, and typically in real vector spaces, complex vector spaces, these are obvious. The vectors are real numbers, there is a natural way to add, there is a natural way to do scalar multiplication. Yeah. But there are other vector spaces, function vector spaces and everything, where these need to be carefully defined. Yeah. We might not see those things in this course, but yeah, just saying. Yeah. Again, yeah, there are finite fields also, where then all the addition will be modulo p. Yeah. Multiplication will also be modulo p. Okay. Yeah. So, okay. So, now we understand what a vector space is. Yeah. So, what is linear independence?
But addition can be anything, right? Like, for example, if it's 3x plus 2y, 3x and 2y is one vector, 3x over 2y. Another vector is, let's say, 2x over 1y. Or let's just say 3x is one vector and 2x is another vector. We can define 3x plus 2x to be equal to 10x. Can we define addition operation by our own means?
No. So, when you say V is a F vector space, V already has a addition operation defined.
Yes.
Yeah, and it should be a group under addition.
Yeah. So, if I say, can I say the addition operation is vector 3x plus vector 2x is vector 10x?
So, whatever addition operation you define, it should form a group. That means there should be additive inverse for every element.
It's not just the normal multiplication, it can be however I define.
I do not think I followed your question, sorry.
3x vector and 2x vector does not necessarily have to add up to 5x vector. I can define my addition operator in a different way.
You can define different way, but it should that addition operation should form a group, yeah, with V. Yeah. And yeah, there are some 8 conditions for V to be F vector space. Yeah, 8 or 10 conditions. I do not want to list that down, and it will be very pedantic and not very interesting. It's commonsensical conditions only. Most of the things it will be like very commonsensical and elementary. Yeah. Yeah.
So with that we can also have fields with non-prime numbers, finite fields with non-prime numbers.
Yeah. So what all kind of finite fields are possible? Yeah, is a very interesting thing. And yeah, it was very detailedly studied by a very young French mathematician who died very early. His name is I forgot. No, no, no. Ghost lived for really.
By duel.
The guy who died by duel. I have his name always in my tongue, but now I just lost it. Yeah, so he actually came with a very big theory. He characterized what all fields, yeah, finite fields can be there, yeah, and came with a very beautiful theory. And I think he died at the age of 22 or something. I think even younger. I don't think he lived till 20. So
Yeah.
Galois. So this entire theory of finite fields is called Galois theory. Yeah, and yeah, it's interesting. So that's an interesting theory on its own. And if you are doing a course on coding theory or something, you will be seeing lot of that. Yeah, how to construct finite fields and everything. So mainly it is modulo prime numbers only. Yeah, but you can also take polynomials modulo some. You can define what is called a prime polynomial also. Yeah, and you can also do a modulo prime polynomial. Yeah, so roughly I am saying without explaining what it is. It's there are more details to it, but yeah. Okay. Yeah, we are coming back to linear independence. Yeah. So yeah, what is linear independence? When do we say a set of vectors are linearly independent?
If a vector is not a scalar multiple of another, then they are linearly independent.
Okay. So we will say a set of vectors, set of vectors, let us say v1 to vk, yeah, v1 v2 up to vk. Yeah. When do you say these are linearly independent? When do you say a set of vectors are, yeah, two vectors are linearly independent when one is not a scalar multiple of the other. I agree with you. Yeah. So yeah.
They sum up to 0, and given that they all are 0, there only one condition exists.
So we will say that
They
S.
sum up to 0 vector, given it only satisfy when they all are null vectors.
Yeah, yeah. So they are linearly independent. Yeah, if yeah, only way to make them sum up to 0 by using linear combinations is if all those coefficients are 0. Yeah, summation of alpha I v I, yeah, equal to 0. Yeah, let us say you somehow do some scalar multiplication and addition and manage to make the sum up to 0. This implies, yeah, all the alpha i's has to be 0. Yeah. Yeah. So only way to if yeah. So a set of vectors are linearly independent. Yeah, yeah. If there is no non-trivial linear combination which makes it equal to 0. Non-trivial meaning some alpha I has non-zero. Now, if all alpha i's are 0, obviously it is 0. Yeah, and that is the only way to make them sum up to 0. Yeah, that is what a linearly independent is. Yeah, and when do you say vectors are linearly dependent?
When there exists some alphas.
Yeah,
Alpha I.
when there is some non-zero alpha I,
Non-zero.
non-trivial alpha I. Yeah, at least some of the, maybe not all, some of the alpha i's might be 0, but at least I mean one or two of them should be non-zero. Yeah. So if a vector set of vectors are not linearly independent, then this it is linearly dependent, that is there is some non-zero alpha i's, not all of them 0, that sum up to 0. Yeah. And what that means is one of the vectors in this set can be written as linear combination of the others. Okay. Okay. So we understand what linear independence is and linear dependence is. Yeah. Yeah. So yeah. So once we understand this, what is a basis for the vector space? What is a basis for the vector space?
vectors with which you can actually span the entire, you can actually express any vector as a linear combination of using only those vectors.
Yeah. So, let us go one by one. I will say first what span is. Yeah. So, given a set of vectors, yeah, what is the span of the set V 1 to V k? What is the span of V 1 to V k?
All possible linear combinations of those vectors.
All possible, the set of all possible linear combinations of vector. Set of all possible linear combinations. Yeah. I don't know, I have to set up some palm rejection or something. It's detecting my palm. Should be some way to do this. I will do it later. Yeah. Okay. So, it is a set of all possible linear combinations. Yeah. So, remember, so we have not said that V 1 to V k are linearly independent or anything like that. V 1 to V k are some vectors, we take all the linear combination, you will get the span. Yeah. The interesting thing is the span of a vector space, span of a set of vectors is a vector space by itself. Yeah. You can take one vector and take its span. Yeah. It is a vector space by itself. Why?
It includes all the possible combinations.
Yeah, you take any. So, let us say I take the vector 1 0, or let I take the vector 1 1. Yeah, I take the vector 1 1, take all the span of that vector 1 1. What is the span of that vector 1 1? Yeah, it is all the points in the y equal to x line. Yeah, all the vectors like alpha alpha, where alpha can be anything. I take two such vectors, add them up. Yeah, no, I will get again a vector same type of vector. Yeah. So, it's the span of this thing is a vector space, because take any set of vectors in the span, take a linear combination, you will get another vector in the span itself. Yeah. So, span is a, yeah, it is kind of like a subspace. Yeah. A subspace is a subset of the vector space, yeah, which is again a vector space by itself. Yeah. Span is a subspace. Yeah. That is, it is itself closed under. Yeah. What happened? Hopefully everything is saved. Yeah. Yeah. So, span is a subspace, that means it is a vector space in itself. You take any vectors in the subspace, it will be already belonging to the subspace. Any linear combination in the subspace will be now. Okay, good. Yeah. So, let us say you have a 3-dimensional space, yeah, and what is the span of the vectors 0 1 and 1 0, sorry, so, I mean 1 0 0 and 0 1 0.
It will be a 2-dimensional plane.
It is a 2-dimensional plane, all the z axis values will be 0, right. You just what about the vectors 1 1 0 and 1 2 0? Yeah, it is the same xy plane. Yeah. So, the span of 1 0 0 0 1 0 as well as the span of 1 1 0 and 1 2 0 is the same. Yeah, because if you add and subtract, you will get the entire xy plane. Yeah. Yeah. Okay. So, we and okay. So, yeah. So, the thing is yeah, you do not get the entire vector space if you just span only these two vectors, right. Yeah. So, let us say I take the vectors 1 0 0, 0 1 0, yeah, and 1 1 0. what do you get? Yeah. So, the span of let us say 1 0 0 0 1 0 and 1 1 0. What is the span? Still the xy plane?
Yes, sir.
Yeah, because actually the third vector is not really needed. It is already first two vectors, if you add, you will get the third vector. Yeah, they are linearly dependent, and so if you have linearly dependent vectors in your set, yeah, span is not adding anything extra. It is not going to add anything extra. Yeah. So, yeah. So, what is a basis now? Now we can talk about basis. What is a basis?
Maximal set of linearly independent vectors that span the vector space.
So, the basis is a set of vectors, yeah, maximal or minimal.
No, it should be maximal, because otherwise if we take one more vector it would be linearly dependent.
I mean, I can take the entire vectors, all the vectors, that will be maximal, no?
So he said maximal set of.
I see.
Maximal
Yeah,
set of
okay.
linearly
Yeah, he said the maximal set of linearly independent vectors that span the entire vector space. Yeah. So, it is very tricky. So, it is maxi.
Above example should be 1 0 0 and 0 1 0, not the other one.
Yeah. Yeah. The maximum sized, I have to be careful when I do maximum or maximal, might be very different things. And definitely know that this is maximum sized is correct. Maximum sized linearly independent, yeah, vectors that span V. Yeah. So, we say a basis for V, basis for a vector space V. Yeah. A basis for a vector space V is the, you take the largest set of linearly independent vectors that span the entire vector space.
You don't have to write that span V, right? Just the maximum size remaining independent vectors.
Yeah, actually that is right. Yeah. So, you do not really need this. Yeah, so, the maximum sized linearly independent vectors actually will span the vector space. Yeah. Because suppose it does not span. So, you have some set of vectors which are linearly independent and it does not span the vector space V. So, there is one vector which is not in the linear combination, add that vector to the set. Yeah. So, it was not maximum in the beginning. Yeah. So, you do not need to say that span V. If you take the maximum linearly independent set of vectors, yeah, in V, yeah, that will span V, because if it does not span V, you can add that one vector which is outside the span and it will still be linearly independent. So, it was not maximum. Okay. Okay, so we understand basis. So, the very interesting thing about basis is, so yeah, now we need to understand what is called dimension of a vector space. Yeah. So, what is the dimension of a vector space?
Number of linearly independent vectors.
Mm.
Size of the space.
Size of basis set.
Yes.
Yeah.
Maximum reconsider.
Hmm. Yeah. So, instead of maximum, let me write maximal. Yeah.
Why? What's the difference?
Yeah, there is a very big difference between maximum and maximal.
What is it?
Yeah. So, yeah, so typically the right example is matchings in a graph. Okay. So, you everybody knows what a matching in a graph is. It is a set of edges that does not share any vertices. Yeah. So, set of edges that does not share a vertex is a matching. Yeah. And the maximum matching and the maximal matching are very different. Yeah. So, you can keep picking edges, right, you can keep picking edges. Yeah. So, let me give some example of graphs where maximal and maximum are very different.
What's the meaning of the two words?
So, maximal meaning you cannot add any more vector and still become linearly independent. Yeah. Maximum means, yeah, among all maximal linearly independent set, it is the set with maximum size. Yeah. So, maybe for because your initial choice of vectors you cannot add one more vector, yeah, because of which it become maximal.
Just take 3 vertices in a line. If you take the between edge, then that's also maximal. You can't add anything else. But you can also take the 2 edges in the corner. That is also maximal. So the maximum is this 2, but this is also maximal.
Yeah. So, yeah, the example he is showing is
3, 3. That's it. No, sorry, 4. Yeah, 4 and 3 edges.
good enough. Yeah. Now, this matching is a maximal matching. I do not know what to do about this. Yeah. So, the matching here is a maximal matching, yeah, because I cannot anymore add edges, it will not become a matching, because of, yeah, I mean all the other edges also has these nodes in common, but this is maximal, this is a maximal matching, yeah, but the maximum matching is actually this. This is a maximum matching. Yeah. So, in matchings, yeah, maximal matching and maximum matching are two different things. Yeah. It is a very good puzzle to solve, that actually the maximal matching should be at least the maximum matching by 2. Yeah, it is a good problem to solve.
Or else you just take the opposite ones.
Okay, yeah, I will leave it as a homework. Okay, any maximal matching has to be a size at least the maximum matching by 2. Yeah, so yeah, okay. Okay, but that is a side story. Okay, I mean, but in vector spaces, yeah, apparently the maximum, yeah, linear independent sized linear independent set is also a maximal. I mean, a maximum size is already a maximal. That's so. But the thing is, any maximal linearly independent set is also a maximum sized linearly independent set. Why? Because suppose you have a maximal sized linearly independent set.
Adding one more will make
Yeah, it already spans the entire vector space. No, yeah, suppose it does not span the entire vector space. Yeah, there is one outside its span, we can add it. So, why was it maximal? It was not maximal. Yeah. So, in vector space linear independence, a maximal is same as maximum. Okay. Yeah. Yeah. So, the interesting things about vector spaces, you can take any two basis sets, yeah, take any two basis sets, the size of the basis set, any basis set has to be the same. Take any basis set, the size of the basis sets has to be the same. Yeah, it is a good exercise to solve. Yeah, prove that suppose you have a basis B which is consists of vectors b1 to bn, yeah, and there is another basis B prime, yeah, which is b1 prime to bm prime. Yeah, so suppose n and m are different, yeah, then you should get a contradiction.
The proof you just stated, maximum is equal to maximum.
Yeah.
Both of them have to be maximal, so both of them have to be maximum also. So if both of them are maximum, then both of them have the same size.
Yeah, so yeah, it's good to actually clearly think and find out. The ideas are already there, yeah, but yeah, proofs it's good to clearly convince yourself, yeah, yeah, okay. Okay, so the dimension of a vector space is nothing but the size of the basis, yeah, size of a basis set. And since any basis has the same number, has the same size, this is well defined. Otherwise, there is a problem. No, this basis has some size, that basis has some size, then how should the dimension be that or this? But that question will not arise here. All bases will have the same size. Yeah. Okay. So we know what dimension is, and I mean it is a natural thing, right? I mean. If the vectors are 3D, then it is a 3D, 3-dimensional vector space. Yeah. Yeah. So, yeah. And next is what is called coordinates of a vector V with respect to a basis B equal to, let us say, B1 up to Bn. Yeah. So, suppose you have a vector space V, yeah, and very big, so vector space will be in capital V's, okay, and vectors will be small v's, okay. Yeah. So, suppose you have some vector space and the basis of that vector space is B1 to Bn. Yeah. So, what is the dimension? N. N is the dimension. Okay. Now, given this vector space, yeah, given this basis, yeah, we can define what are the coordinates of the vector with respect to a basis. Yeah, what is that?
The scalars which each of those vectors and bases.
The coordinate is basically linear
The
combination
linear
of the
Yeah. So,
elements of basis.
so V is in the span of B. Yeah. V has to be in the span of B because they span the entire vector space. Yeah. So, V belongs to the span of B.
And B
Yeah.
should also belong to span of B.
No.
Should we say that?
How? I mean V is only a single vector, no. Span of V is only that one dimensional thing, it is only a line, right. So, no, that does not mean anything. Yeah. So, span of one vector is just a line, it is a one dimensional vector space. Yeah. If you yeah, this is also a good problem to solve. If you have the span of k vectors, the dimension of that will be less than or equal to k. Yeah, very reasonable thing to say, right. I mean yeah, you cannot span more dimensions than the number of vectors you have. Yeah, but it can be less. For example, like I take a V1 and 2 V1 and 3 V1 and take the span. What will be the dimension? 1, because with 2 V1 and 3 V1 I could already get from V1. Yeah, is that fine? Yeah. Okay. So, suppose V belongs to the span of B because B is a basis, it spans everything. Yeah. So, there is a linear combination, V is summation over I equal to 1 to n alpha I,
So, it's a small v.
yeah, small v,
Vector.
yeah, small v, yeah.
I was thinking that vector.
Oh, I see, okay. Sorry, yeah, yeah. So, V belongs to the span of B.
If
Yeah.
it was capital V,
Mhm.
vector space, then we can
It's equal.
then
you cannot say belongs to. Span of B equal to capital V. Yeah. So, belongs meaning it is inside the set, equal meaning the sets are equal. These are two different things. Yeah. Okay. Is that clear? Yeah. So, belongs mean that is a member of the set. Yeah. Equal meaning that sets itself are equal. A span of B equal to V, equal to capital V, and small v belongs to the capital V. So, it also belongs to span of B. Okay. So, V has a linear combination of Bi's which gets that V. Yeah. The interesting thing is the alpha i's are unique. You will not have another alpha I which also gives V. Why? Suppose this was also V was also obtained by summation over I equal to 1 to n beta I B I.
Subtract the two, then you get that there is a linear.
You get a non-dependence
between the vectors.
Now, you subtract the two equations. So, you will get that alpha I minus beta I into B I summation is equal to 0. What does that mean?
They should be equal.
That means B i's are linearly dependent.
No, that means all bi's have to be 0. Oh, sorry, all alpha i's minus bi's has to be 0.
Yeah,
That means
either alpha I has minus B I has to be equal to 0, or if it is non-zero, B i's are linearly dependent, but they are linearly independent. So, the second case does not arise. So, alpha I has to be equal to beta I. Yeah. So, that is alpha I is unique. Yeah. So, if you have a linearly independent set of vectors, yeah, and it linearly so and its linear combination gives a vector, that alpha i's are unique. Only one way can a linearly independent set of vectors, yeah, give another vector by linear combination. Yeah. So, this implies that alpha I equal to beta I for all I. Yeah. So, every vector, yeah, is given by a unique linear combination of the basis set. Yeah. And the scalar corresponding that unique linear combination is called the coordinates of that vector with respect to that basis. Yeah. So, if I take this thing alpha 1, alpha 2 up to alpha n, this is the coordinates of V with respect to B. Yeah. Yeah. Given a basis set, you can give a coordinate to all the vectors in your vector space, a unique coordinates. Yeah. Now, I mean for example, okay, 3 dimensions. Yeah, I take your basis set 1 0 0 0 1 0 0 0 1. Yeah, and that is the natural standard coordinate system, right. The vector 2 3 4 is nothing but 2 into 1 0 0 plus 3 into 0 1 0 plus 4 into 0 0 1. Yeah. So, that satisfies this, but now you can think of another basis set. Yeah. For example, maybe my basis set is 1 1 1 1 0 2, I mean yeah, maybe some third other vector. I need to find a linearly independent vector. I cannot say that on top of my head. Yeah. So, 3 another vectors I can choose. With that as the basis, you will get another set of coordinates for the same vector. Yeah. So, what we are saying is we can set our x y z. Yeah. We can choose a different x y z coordinate system for all the vectors in the vector space. Does not need to be the standard. I mean, initially you might have one standard, yeah, then you might want to change the basis to another basis set and then look at the coordinates. Yeah. And that is what we were trying to do earlier, right. We had like one coordinate system, you had the galaxy x y z all were taking large values. We suddenly change the basis to that particular x y z. Yeah, I take those vectors as my basis set. Suddenly the set values are all very minute, the set coordinates does not really matter. Same thing in that images also we saw. we need to find a different basis, yeah, which where I mean the lateral coordinates are irrelevant. We want to find the most interesting basis vectors along which there is maximum variance in the data. Yeah. Yeah. So, now we have a way of speaking about that problem mathematically. Yeah. We want to find a basis set, yeah, in a ordering. So, B 1 should be the vector according to which there is maximum variance in the data. B 2 should be another vector, yeah, which again something I will define, orthogonal to B 1 at 90 degrees to B 1, where there is next maximal this thing, yeah, and B 3 similarly we want to go on selecting B 3, we want to add ordering, yeah. And then maybe after B 5 I will just ignore those bases and I will only look at the coordinates in B 1 to B 5, that is what we want to do. Yeah. Okay. So, we understand what coordinates are. Yeah. Now, okay. So, now let us look at what is called a linear transformation. Yeah. So, how much time is there, a clock or watch or something? 3:05. Okay. Yeah. Okay. So, yeah, let us go over some basic terms, let us just get comfortable with it, that is all today's lecture plan is. Yeah. So, what is a linear transformation?
Transformation of a vector by a matrix.
So, the basic definition of a linear transformation is a function. Yeah. It is a function from one vector space to another. V is one vector space, all the capital letters are vector spaces. V is one vector space, W is another vector space. It is a function from one vector space to another. Yeah. Not any function can be a linear transformation, it has to satisfy some properties. What is the properties?
F
Okay.
F of say alpha v should be equal to alpha of f v, if I remember correctly.
Yeah. So, yeah, so for this to work, yeah, we need a few things. We need V and W to be F vector spaces. Both of them is vector spaces with respect to the same field. Yeah. V comma W are F vector spaces. Yeah. Linear transformation does not work if one is a real vector space, another is a complex vector space. No, both of them has to be real vector spaces. Okay. Yeah. So, V is a real vector space, scalar comes from real numbers. W is also a real vector space, scalars come from real numbers. Yeah. So, now this condition makes sense. F of alpha times V is alpha times f of V. Yeah. F of V is some element of W, and W is also a F vector space. So, you can multiply with scalars from F. Okay. Yeah. So, is this the only condition?
There is additive and integrative also.
So, if you do f of alpha f of V plus W, yeah, should be equal to f of V plus, yeah. Basically, it should play nice with both the operations. Remember, in a vector space there are two operations, one is the addition within the vector space, another is scalar multiplication. Yeah. And what this condition says is, you can do the addition or scalar multiplication first and then apply the function, yeah, or you can apply the function and then do the addition and scalar multiplication, it should be the same. Yeah. And typically these you say in one go, right. You say that f of alpha v plus beta w should be equal to alpha times f of v plus beta times f of w. Yeah. So, we are saying 1 and 2 together in one go by doing the third condition. Yeah, all these things are not necessary, if we just say the third condition, it is enough. So, a linear transformation is a function between two vector spaces which plays nice with the scalar multiplication and addition of the vector space. You can do it before or after, it does not matter, applying the function. Okay. So, we know what a linear transformation is. So, so for now let us look at linear transformation from the same vector space to itself. Just for now, okay. We are let us say we are looking at linear transformation from the same vector to itself. So, these are typically called operators, because you are getting back another element of the same vector space. Okay. So, so given a linear transformation like this, and if you fix a basis for the vector space V, so if I fix a basis for the vector space V, V has a basis B, let us say B1 to Bn. If you fix a vector space, a basis for a vector space, then every linear transformation becomes a matrix multiplication. F of V is same as there is a matrix which represents F and B and times this will be the coordinates of V with respect to B. So, given a let us say you have some real vector space, you have a vector space where the scalars are coming from real numbers. Now, if you fix a basis for that vector space, now you can look at the coordinates of all the vectors. Or the original vector space might not be composed of real numbers or anything, it can be some arbitrary stuff. But once you fix a basis, your vector space will consist of tuples of real numbers. The coordinates of every vector is nothing but a tuple of real numbers, right. So, if you have a real vector space and if you fix a basis for it, your vector space essentially becomes real column vectors. So, a abstract vector space consists of vectors, they are not nothing to do with real numbers or anything, some abstract elements of the set. But once you fix a coordinate for that vector space, once you fix a basis for that real vector space, you will get real vectors out of it, which is basically the coordinates. The alpha is corresponding to every vector will be the coordinates, and remember alpha is a real numbers. So, after you fix a basis, you will get the coordinates for every vector. And after you fix the basis, every linear transformation will become a matrix.
Matrix of those coefficients.
What that matrix is, again there is a nice structure to it. I will give a reference, you should definitely look at it. It is a very interesting matrix. So, if you want to apply f, the linear transformation f to the abstract vector V, it is the same as multiplying the matrix M to the coordinates of V with respect to B. So, once we fix a basis, every vector gets some coordinates and every linear transformation gets a matrix. And now you only work with this matrix and this coordinates. The vector space becomes like your usual tuple of real numbers, and linear transformation becomes matrix multiplications. Okay. So, this distinction between abstract vectors and abstract linear transformations and matrices and coordinates you should understand. A linear transformation is a matrix with respect to one particular basis, and actually if you change the basis, the matrix of the linear transformation also change. Maybe one linear transformation is very complicated in one set of bases, and maybe if you change the basis, that linear transformation will become simple. Yeah. So, a very important thing that happens in linear algebra is given, let us say you have some linear transformation. Yeah, it might be your initial coordinates might be in some standard basis or something like that. Yeah. Maybe there is another basis in which that linear transformation becomes very simple. Yeah, and if you, instead of doing this, if you change the basis to that basis, yeah, change the coordinates to that basis, this thing, suddenly the linear transformation will become very simple.
Simple as in some coordinates become 0, some entries become 0.
Maybe lot of entries become 0. Yeah, maybe the runtime you can easily compute that linear transformation and everything. Yeah.
So that's the point when we do reduction. So we are basically simplifying the methods.
Yes. Yeah. So you might have heard of some very popular linear transformation which you have heard of. Yeah, can you tell me a very popular linear transformation? I am pretty sure everybody has heard of it. Your engineering mathematics is the first thing that stares at you. Fourier transform. Yeah, Fourier transform is a linear transformation. Yeah, and it is actually changing a basis to an interesting basis. Yeah, and then lot of linear transformation becomes very simple. Yeah, I mean this course will not go into all those details. Yeah, but it is a good time to revise what Fourier transform is and everything in this setting. So, yeah.
When we transform vector space V to W,
Mm-hmm.
do we change the dimensions of V?
Yeah, I mean you can have linear transformation within between different dimensional vector spaces. Yeah. For example, I mean I can have a linear transformation from R3 to R2. Yeah. For example, okay, I just drop the z coordinate. Yeah, I will just take x, y, c and only have x, y. Yeah, or I can convert x, y, c to 2x plus 3y. Yeah, these are all linear transformations. I mean you can verify that this condition is satisfied. Yeah, you need to verify that this condition is satisfied. Yeah, you need to, let us say you have a function which maps input x, y, c to 2x comma 3y. Yeah, does that satisfy this condition? Yeah, it's yeah. So I am defining a function, yeah, from R3 to R2. Yeah, the function is f of x y c, yeah, equal to 2x comma 3z. This is a linear transformation. How do we verify? Take two vectors. Yeah, let us say v is x y c. Yeah, and let us say w is x prime y prime c prime. Yeah, and what is f of alpha? So yeah, let us do f of alpha times v is how much? It is basically 2 alpha x plus 3 alpha c. Yeah, this is also equal to alpha times f of v. So this is verified. Yeah. So what about f of v plus w? Yeah. So what is v plus w is x plus x prime, y plus y prime, c plus c prime. Yeah. So this will be 2 into x plus x prime, 3 into c plus c prime. That is the definition of f of x y c. No? Yeah. Now this is also equal to 2x comma 3c plus 2x prime comma 3c prime. Yeah, and this is nothing but f of v plus f of w. Yeah. So, you need to do this verification. Yeah. Whenever you say something is a linear transformation, you need to do this verification, yeah, that this actually indeed is true.
Perceptron do the similar thing. Perceptron and ML you study. Essentially, it transforms the n-dimensional vector to R. And itself a linear class.
Yeah. So, you can have a function which transform r raised to n to real numbers, that can be a linear transformation.
And that is.
Yeah. So, you can have, yeah, dimension reduction can happen. Yeah. Yeah. So, yeah, I mean, yeah. So, yeah. So, you can.
This summation we can do.
Yeah, all these are linear, as long as it satisfies this condition, it's linear transformation. Yeah.
If there is f of v, like shouldn't we say that would be coordinates of f of v with respect to b prime, like some other basis?
No, no, I didn't have any basis here.
No,
So,
no,
here the, I mean, here the input vector space is R3.
I'm talking about here when you wrote m times coordinate. Here it should be coordinates of f of v with respect to b prime if b prime is the basis for the.
Yeah, yeah. So, you are saying this thing, yeah, f of x, the coordinates of the coordinates of this, yeah, you are right. Strictly speaking, I should write that. Then the coordinates of f of v with respect to the basis b, yeah, will be equal to the matrix of the function with respect to that basis times the coordinates of the original vector. This is what you are saying. Okay. Yeah. So, I mean, remember, when you fix a basis, every vector becomes the vector of real numbers, the coordinates. Yeah. So, the m of matrix multiplied by this is also a column of real numbers. Yeah. So, that is also a coordinate with respect to the same basis. Yeah, thanks for pointing that out. Yeah. So, how much time do we have?
10 minutes.
Yeah, 10 minutes. Yeah. So, let us finish today with okay. So, now we understand what a linear transformation is and what is a matrix of a linear transformation is. Yeah. Yeah. So, there are yeah, let us assume that okay, there is one basis, there is a vector space, there is a basis. So, a linear transformation has a matrix. Yeah. Now, yeah, it does not have to be a matrix, but yeah, there is a linear transformation. So, there are two subspaces which are related to the linear transformation. There is what is called the kernel of a linear transformation. So, let us say f is a linear transformation. Yeah. What is the kernel of f? Yeah. It is a set of v belonging to the input vector space, yeah, such that f of v is equal to 0. Yeah. It is a set of all vectors where the linear transformation produces a 0 value. Yeah. The claim is this is a subspace. Why?
The dimension cannot increase on a linear transformation. Dimension of w cannot be greater than dimension of v.
Yeah, but I mean, why should this be a subspace of V? Yeah, the claim is this is a subspace of V. You say subspace of V.
Take v and w as.
Yeah. So, how do you verify something is a subspace? Take some vectors there, take linear combination, check if it all belongs to the same set. Yeah. So, suppose you have two vectors in the kernel v and w. Yeah. That means f of v and f of w is equal to 0. That is the definition of kernel. No, v and w belongs to the kernel, meaning f of v has to be 0, f of w has to be 0. Now, I take alpha times v plus beta times w. Yeah. Now, you take a f of alpha times v plus beta times w. Since it is a linear transformation, it has to be equal to alpha times f of v plus beta times f of w. Yeah. But f of v and f of w are 0. So, this also is equal to 0. So, that means alpha times V plus beta times W also belongs to the kernel of F. Yeah. So, this is a subspace. Take linear combination of vectors in the kernel, you will get another element of the kernel. Yeah. This only works if F is a linear transformation, right, because you take linear combination, then you have to apply F, F has to go inside the scalars and then you make that argument. Yeah. So, for a linear transformation F, yeah, this becomes a subspace. Yeah, it is very important that F is a linear transformation, then only this will work.
Why it is 0?
Sorry?
Kernel is always 0.
No, I did not say kernel is always 0. F of V is 0. Its definition is that. Yeah. It is a set of vectors where the function value is 0. Yeah. It is a 0 vector, F of V meaning it is a 0 vector. See, F of V is a element of W, okay. Yeah. W is under vector space. Yeah. Every vector space has a 0 vector because it is a group under addition. Yeah. Every group under addition should have a 0 element, it is a 0 vector. So, for example, R2 the 0 vector will be 0 0 vector, R cube the 0 vector will be 0 0 0 vector. Okay. Yeah. So, actually this is the 0 vector, I should just mention that clearly. This is not the normal 0, it is actually a 0 vector. Yeah.
Kernel gives you the null space.
No, no, null space is null space. 0 vector, null space, these are two different things. Yeah. There is a vector, every vector space will have a 0 vector. Yeah, that is the vector where you add any other vector to it, you will get the same vector. Yeah. So, kernel is a set of vectors in the input space, yeah, which maps to the 0 vector in the output space. Yeah. So, you have some input space which is V, there is some output space which is W. Yeah. There is a 0 vector here, yeah, there is another 0 vector here. Yeah. It is a set of elements in here which actually a 0 vector always map to the 0 vector if it is a linear transformation. Yeah. The set of elements in the V which is a subset of V which maps to the 0 vector in W, yeah, is the kernel of the linear transformation F. Yeah. Null space is another name for kernel. Okay. So, this is also called the null space of F. Okay. So, this is a subspace, we have established that. Yeah. Now, another space is called the range of F. The range of F is a subset of W, it is a subset of W. I mean, everybody remember old functions, no? What is the range of a function?
Subset of code that actually.
Yeah, it is the yeah.
Set of outputs.
Yeah, it is basically a range of F is the set of W belongs to W, yeah, such that there exists V, yeah, such that F of V equal to W. It is a set of elements. So, I define a function from real numbers to real numbers, yeah, where the function is let us say only modulus of x. Yeah. What is the range of the function? Non-negative real numbers. Yeah. Just because a function is defined from real numbers to real numbers does not mean it will actually have all the numbers as in the range. Range is a subset of the output, yeah, where actually some input maps to it, yeah, because it might not be a on-to function. On-to functions map to everything in the range, but it might not be a on-to function. Yeah. So, the range is a subset of W, that is very clear. It may not be equal to full W, but it may be subset of W. Yeah. The interesting thing is range of F is also a subspace of W. Yeah. I will leave it for you to prove at home. Yeah. Yeah. Why is the range of F a subspace of W? Yeah, we proved that kernel of F is a subspace of V, yeah, and actually the range of F is a subspace of W. You need to prove it. how do you prove it? You take two elements in the range of f, take the linear combination and show that it is also in the range of f.
Could you repeat the proof for kernel is a subspace of this?
So, there is only way to for proving one something is a subspace. Take two vectors in that space, take a linear combination, show that the linear combination is also in that same space. Yeah. So, you take a vector v which belongs to kernel of f, that means f of v equal to 0. Take another vector w which belongs to kernel of f, that means f of w is also equal to 0. Now, you take the linear combination alpha times v plus beta times w. Yeah. Now, let us apply f on it. F of alpha times v plus beta times w is a linear transformation. So, it is equal to alpha times f of v plus beta times f of w, but we know already that f of v and f of w are 0. Yeah. So, f of alpha times alpha v plus beta w is also equal to 0. So, alpha v plus beta w belongs to the kernel, that is it. We just follow definitions, that is it. Yes, similarly, we need to show that if v belongs to range of f and w belongs to range of f, alpha times v plus beta times w also belongs to range of f, you need to show that. Yeah. Okay. And finally, I stop with one important theorem. Okay. So, suppose you have a vector space V and you have a linear transformation from a vector space to itself. Yeah, it is a linear transformation to a vector space to itself. Yeah. If you look at the kernel, if you look at the dimension of the kernel, remember kernel is a subspace. Yeah. So, I can define dimension of the kernel. Yeah. Kernel is a subspace, so it has a basis. Yeah. Size of the basis set is the dimension of that kernel, and I can define the dimension of the range. Range of f is a subspace, it has a basis, size of the basis of that range subspace is called the dimension of that range. These two are well defined quantities. Yeah. This apparently will be equal to the dimension of V. Yeah. So, this is called the rank nullity theorem. Yeah. And it is not very complicated to prove. Yeah. I suggest that you go over the textbook. It's yeah. No, no. Here the linear transformation is from V to the same vector space.
From V to same vector space, then dimension of kernel has to be 0. Dimension of range has to be
Why dimension of kernel has to be 0?
because it's the same vector space.
So let us say you have so let us say we have this function, right. Yeah, I am defining let us say this function as I am defining a function from R3 to R3 where f of x y z is 2x plus 3z comma 0. Yeah, this is a linear transformation. Yeah, it is a linear transformation from the same vector space to itself.
No,
it is
not to the itself, because the vector space of the V is
so the codomain might not be equal to the range. That is what I am saying. I am just telling the example of absolute value, right. Absolute value is a function from real numbers to real numbers. Yeah, but the range is only positive real numbers.
But by definition, vector space is the space which is spanned by the vectors. For 2x comma 3z do not span V. So V is let us say the all 3 dimensions x, y, z, any 2x by definition V is the space which is spanned by the vector, the base.
See, the only problem here is, see, f is a function from R3 to R3. Do you agree? So, f is input to f is a 3-dimensional vector,
Yes.
output to f is a 3-dimensional vector.
Yes.
So, it is a function from R3 to R3.
Okay.
Right, it is a function from it is not a on-to function, I agree, it is a many one function, yeah, it is a many one function, yeah, it is a many one function, it is not a on-to function, it will not get all the values in R3 and the output, it only takes values where c coordinate is equal to 0, yeah. Now, so what is the I mean yeah, what is the range of f?
That is the plane.
It is the xy plane,
Exactly.
yeah, the range of f is the
Exactly.
no xy plane, because only this last coordinate is 0.
You wrote 2x over 3z.
Yeah, but 3z is in the second coordinate, which is the y coordinate.
Okay. Yeah.
Yeah, yeah. So, the range is actually the xy plane. All the c coordinates are 0 in the range.
That is fine, but over
Yeah.
here in the right side you wrote f is a map from vector space V to vector space V. So
Yes.
f of V should also the vectors in f of V should also span V by definition.
No, no, not necessary. Why should do that? It can be a on-to, it can be a many to one function which is not on-to. Yeah, like this example. Yeah, yeah. So you can have a many function which is not on-to. That is the whole point. Actually, that exactly your point is what that theorem is also saying. Yeah. So if you take the dimension of range of f, yeah, it might be much smaller than V. Yeah. But if you add the dimension of kernel to it, you will actually get the dimension of the vector space. Yeah. So it is a very important theorem. It's very commonsensical only. Yeah. If you look at the proof, but I want you, I will give you the reference. I want you to go over the proof yourself. Yeah. We could discuss it again next lecture, but I want you to go over the proof, yeah, and try out many of these examples. I will give you exercise in the textbook, please try out. Yeah, we need to refresh this so that we can understand all those arguments better. Yeah, we will change the basis, we will change the coordinates, then we need to understand yeah, how does the basis change. Yeah. So yeah, that's all for today. I can take questions.
Sir, this rank nullity theorem.
Yes.
So there is one more definition I was remembering
Mhm.
from
Yeah.
my linear algebra course. Like dimensional kernel of f
Mhm.
essentially give the null space.
Dimensional kernel is same as the null space.
Yes, and
Dimension
dimensionality of range of f gives the number of linear independent vectors.
So another way to state it is, yeah. So this thing is also called the nullity.
Yes.
The dimension of kernel of f is called the nullity, yeah, and the dimension of range of f is called the rank of f.
Yes, rank.
Yeah, a rank of a matrix is basically same as the rank of the linear transformation corresponding to the matrix. Yeah, is basically the dimension of the range of. If you do a matrix multiplication, that is a linear transformation. Yeah, and it is basically the dimension of the range of that output. Yeah, and that is called the rank of that matrix. Yeah, and nullity of the matrix is basically the set of all vectors which the matrix takes to 0. Yeah, takes to a 0 vector. Yeah, and for any matrix M, yeah, if you add the rank and nullity, you will get the dimension of the vector space. Square matrix. Okay.
So what is the set of vector that takes to 0? What was that?
Kernel is the set of vectors that the matrix takes to 0.
Yeah.
Yeah, that is the definition of kernel. No,
Right. Yeah.
the set of vectors that the matrix takes to 0.
If your output is vector space is W, it's different.
Mhm.
This theorem will hold.
I mean W. Okay. I mean some version of it will hold. I need to state it in the right way. But typically this theorem is stated for square matrices. Yeah. I think this theorem makes sense only for square multiple. Possibly you can say something also for non square, but I mean that can be derived from this. Yeah. So, if V and W, so the range dimension of range is going to be something less than dimension of W, yeah, and dimension of kernel is going to be something less than dimension of V, then it becomes complicated to, yeah, I mean let us assume it is square only. Yeah, I think this theorem is typically stated for square only. Yeah.
Otherwise, we'll have issue in.
So, let us typically your W would be a subspace of V itself. Typically your W will be a subspace of V itself. Yeah. Then you think of that linear transformation as from V to V itself. So, only goes to W only, the range will be a subset of W only, but you can consider it as a, I mean for any function from real numbers to real numbers, you can also consider a function from real numbers to complex numbers. No, it is not a onto function, but yeah, it is for a square, let us say the domain and range is same. Okay, so we have kind of revised linear algebra. Yeah, so next lecture I will cover some theorems regarding symmetric matrices. Yeah, symmetric matrices and linear. So we already, I think eigenvectors were already covered, right? Yeah, eigenvectors were already, yeah, some idea about eigenvectors.
This idea was given.
Yeah. So then I will define what eigenvector is, and symmetric matrices have some interesting eigenvectors, some interesting properties related to eigenvectors, and we will also define called orthogonality, which is this you need to define dot product and everything. Yeah, yeah, we will see in the next lecture. Yeah.
It holds for like from V to W, but that remains the same equation.
That's what I said. Yeah, online it says V to W only. I checked it. Because online it says the definition of linear transformation is that when you're saying a linear transformation from f is mapped from V to W.
No, so I
W
don't
can be
know.
V,
But W can be V. Yeah.
but
It's a subset of
W is not necessarily V.
Yeah.
So there is a problem here. No, I mean let us say you take this linear transformation.
What you're saying also is correct. It's just by definition how you're defining the linear transformation. You're defining the linear transformation that the vectors don't have to span W, but by definition.
Yeah.
you have to.
So my worry is, let us take V and W to be different. Yeah. So let us take this particular function. Yeah. It is from R3 to R2. Yeah. So it is converting a 3-dimensional vector to a 2-dimensional vector. Yeah. Now what is the kernel? So the range is basically all of R2 itself.
Yes.
Yeah. Range is basically 2 itself. Dimension of range is 2 itself.
Yes.
Yeah. And what is the dimension of kernel?
1.
What is what is the kernel?
So, can you think like z coordinate is mapping to 0 only?
No, so let us understand what the kernel of the function is. Can you tell me what the kernel of the function is?
A comma B comma C where C is not equal to 0. Any
Why?
point which lies on A comma B comma C where C is not equal to 0.
If C is equal to, so okay, you take A comma B comma C, you will get 2A plus 3B. It is not equal to 0 vector, no?
Any point A comma B comma C where C is not equal to 0 is the kernel of this.
So let us say I take 1 comma 1 comma 2.
Yes.
Yeah. If I apply the function, I will get 2 comma 3. It is not the 0 vector. This has to give the 0 vector, no? Yeah, we are just clearing doubts. Yeah. You need to press that button and open. Yeah. So
0 comma a comma 0.
sorry.
0 comma a comma 0. Because then
See, the value of the function has to be 0.
Sorry, A comma B comma C where A and B are equal to 0.
Huh.
sorry.
Yeah, I mean let us say the function is ABC, I mean the input is ABC, I mean the output of the function is going to be 2A plus 2A comma 3B, which has to be 0. That means A and B has to be 0. Yeah. So it is all the set of vectors, but the set coordinate is no A and B is 0, but the set coordinate is non-zero. What is the kernel? It is a set of all vectors where a and b equal to 0, but the z coordinate is non-zero. That is all the vectors in the z axis, all the points in the z axis.
A and C and are 0, B not equal to 0. Right?
Yeah, because you changed that.
So yeah, that's right. All points in the y axis.
Actually, even you don't even need the condition on A and C. It's just that B has to be non-zero, because you can have in the kernel space.
No, a and c has to be 0, otherwise it won't the 0 vector.
There doesn't have to be a condition on the other thing. Like you don't have to have a condition that something has to be 0. It's just
It
that
is-
something has to be non-zero. What's the condition you're saying for kernel space?
So I am saying that the kernel of f,
Could you just write like 2x over
yeah,
3y?
the kernel of f, the claim is, what is the kernel of f? It is a set of vectors a, b, c such that a equal to c equal to 0.
It has to be, otherwise it won't be give 0.
Yeah,
Yeah.
this is the kernel. And what is the dimension of the kernel?
1.
What is the dimension of the kernel?
He belongs to R3, right? So it has to.
Yeah, what is the dimension of the kernel? See, a and c is equal to 0. So, this is a set of vectors 0 comma 0 comma c, where c belongs to real numbers, right?
0, b, 0.
So,
Because
so,
that's why it is a
yeah, sorry, 0 comma b comma 0, you are right, sorry.
It's very confusing.
No, I think we need to get over these confusions. I mean, it's important that.
Confusion is arising because we define function as 2x over 3z.
Then no, it's, but that is needed. All these functions, a little bit confusion is needed, and confusion need to clear. Yeah, then only we will understand. Yeah, yeah. So you agree that these are the same sets.
Yes.
These two are the same sets. And what is the dimension of that set? Sorry, b belongs to real numbers. Yeah. B belongs to R.
Not b belongs to R, it's just b not equal to 0. That's more precise.
No, b can be 0 also.
That's not belonging to the kernel because
Why?
It will also give 0. If B
B is 0 is also the 0 vector will always be mapped to 0 vector. If it is a linear transformation, 0 vector will always be mapped to 0 vector. Otherwise, it is not a linear transformation. Yeah, yeah. So
dimension is, can we say dimension is 1?
yeah, dimension is only one parameter is there, na. So I take what is the basis for this? 0 1 0 is the basis. You can span all the vectors in this vector space by taking scalar multiples of 0 1 0. This is nothing but the y axis. Yeah. So you should solve enough problems and be comfortable with all this. Yeah, because when you read papers as well as when we come to later arguments, we won't stop to explain all these minute details. Yeah, this thing you should kind of internalize. It should be like you should immediately be comfortable with it. Otherwise, we will get confused in simple things. Yeah. So, in the first 1 or 2 lectures itself, we should solve enough problems and we get comfortable with this. It's very important. Yeah. Okay. So, so the kernel, the dimension of kernel, the nullity is 1, right? The nullity is, this quantity is 1. What is the dimension of range? 2. And so 1 plus 2 is 3.
yes.
So, you have to put the dimension of the domain.
Yes. So it's just a difference of how you've defined linear transformation. You've defined linear transformation as f is a linear transformation from V to W.
So, you are right. I can put this W and I can just put this to be V. You are right. This thing works.
Now, if it is V to V, then function has to be bipartite, because now the dimension of kernel has to be 0. So it has to be 1 1.
I did not follow.
Now,
Sorry.
Now, special case of rank nullity theorem is if f is maps from V to V.
Okay.
What we wrote before. Now that's a special case.
Operator.
That's a special case.
Uh-huh.
That means the function has to be bipartite.
Bipartite meaning?
1 1 and on 2.
Why?
sorry, not bipartite, sorry, bijective.
Why it has to be bijective? No, rank nullity theorem is true. It's just this.
Yeah,
It doesn't.
no, this is true. This
Yeah.
is now I'm saying is another special condition. You wrote F maps from V to V, right?
Then also this is the rank nullity theorem.
Correct. That is the rank.
Yeah.
Now, over there, when F maps to V, then, because that's a special condition, there are special conditions are that F has to be bijective.
No, no special conditions needed.
Not needed. Just saying, F has to be bijective. F will be bijective.
Not really. I think everything is stated in this itself.
This is the rank nullity theorem, yes.
Even when W equal to V, everything is stated here.
Yes, this is correct. Rank
Yeah.
nullity theorem. I'm just saying when F maps from V to V,
Yes.
that's a special condition, special case. Leave rank nullity theorem. You get that F has to be bijective.
Why F has to be bijective? You can have a function f V to V where it's not bijective and still rank nullity theorem holds. It might not be a one-to function.
Rank nullity theorem will always hold. No matter what, in any linear transformation, rank nullity
Yeah, it
theorem
can. F function f can be on. Need not be a one-to function. No, need not be a bijective function.
if F maps from V to V, it has to be bijective.
No.
So in this example,
Why should we saw example? No.
That's not F mapping from V to V.
Yeah, R3 was mapping to R3 itself.
This
If
is not.
no, so take the third coordinate to be 0.
take the third coordinate to be
Then
0.
also you'll get 1
So
plus
that's
2
the thing,
equals.
right? That's a definition which in linear transformation, which is different from the online or textbook definition. It says that when you're this you can't write R3. You have to write R2.
Why? You can write R3 here.
Because
The output is a real three-dimensional vector.
No, over here you can't say F maps from V to V.
You can.
You can't.
You can.
If you could say it here, then you could have said it there. Here also you could have written, right? F maps from V to V. If you can write over here F maps from V
See,
to V.
like a function's codomain need not be equal to range. A function can be need not be bijective. A functions can be like need not be onto.
No,
Yeah, and your statement is stated for all functions.
yeah, not talking about function, talking about the linear transformation. You can't. I think. I'm not sure. You cannot say that F maps from V to V in this particular case.
We can.
If F is a linear transformation.
We can. The only condition for a linear transformation is f of alpha v plus beta w has to be alpha times f of v plus beta times f of w. That's the only condition.
No, but I think by definition, I'm not sure. By definition, I think in linear transformation, when you say F maps from V to V, the F of V, the basis of the F of V should also should also span the
No.
should also span V.
No. That's the whole point of the rank nullity theorem. The range of v, the range of f might not be equal to the entire function.
That's why over here now you did not write V. That's why you wrote V to W. Else, if what you're saying was true, then we could have just written F maps from V to V in the.
We can write.
But we just changed that, right?
No. So I mean,
it's
so
more
there.
general.
This is a more
Let's
general
take the
statement.
Specific version of it. That's what. That's a subset. No, like
Yeah.
you can take W equals V. This is more general.
Then
Yeah.
why will you take W? You can always take V because W has to be a subset of V.
No, so like
Then always
that,
take
that depends on the context.
W
If you
need not be a
want it-
subset of V. That's the whole point, right? W say like V and W are F vector spaces. Yeah, these are abstract vector spaces. W could become other vector space completely.
So he needs to. say-
Both V and W may not consist of real vectors. It might be some other vector completely. Yeah, and still this theorem is true.
And so dimensionality of W should be less than
Huh.
dimensionality of V.
So if you have a function from something to this thing, I mean
Integration.
yeah, dimensionality has to be less.
Increase
Yeah.
the dimension.
I mean, no, you can have a function from V to W where W also has large dimension, not a problem.
Larger than V.
Yeah.
I can put any number of zeros here,
Linear transformation.
right?
That is a linear transformation.
I can have a function R3 from R raised to 100 by putting lot of zeros here, right? I can put lot of zeros here. I can have a function from R raised to 3 to R raised to 100. I put lot of zeros here, or I just repeat 2x, 2x, 2x 98 times. And it's a function. That's a linear transformation because it satisfies all the conditions.
And sir, will they not contribute to dimensionality of kernel of it?
It will not.
0, 0, 0.
It will not. That's the interesting thing. You should verify all this. Yeah. So if I can put 97 2x's here it will not contribute to dimensionality of kernel of f. Kernel of f will remain the same. That is the interesting thing. Yeah. So, yeah, you should get comfortable with the definition. Okay, I mean, yeah, I mean, V and W are any vector spaces. They have to be scalars from the same field. That is the only condition. And f is a linear transformation. That is the only condition, and this is true.
So for clarity, can I just ask you a question? Just like yes or no answer. W can have a dimension greater than V?
Yeah, I already told you. I can have R3 to R raised to 100 by saying there are 97 2x's after this.
Yes. So W dimension, second thing is if W dimension if it's less than V, if W dimension is less than V, can we still write F maps on V to V?
Can we, I mean,
if F of V spans let's say W, so can we still instead of writing that V to W, can we still write that V to V? Because you said the codomain is not equal to range.
could you repeat the question again? Sorry.
F of V precisely maps W, so precisely spans W.
It's a, I mean, basically you are saying it is a onto function. Yeah.
Yeah. So can we? So if R3 maps to R2, F of if there's a function, there's a linear transformation F which maps from R3 to R2. Can we also say that linear transformation F maps from R3 to R3?
So that is a different linear transformation.
The same linear transformation.
I mean, you can define a different linear. So the moment you, when you define a function, the domain and the codomain is fixed.
Yeah.
Yeah. Of course, you can change the codomain. So then it's a different function where it is. I mean, you can define a different function based on the old function.
Okay, so you just have to add zeros manually. You have to like R3 to R3 manually have to add.
You can do all sorts of things. You can
if you
the
f of x comma y comma z is equal to 2x comma 3z, that is R3 to R2.
yes.
If you just add that 0, then it becomes R3 to R3.
Yeah, and you can also have R3 to R raised to 100 also. You put lot of zeros there, and you can get a R raised to 100 vector. Yeah. The thing is, f can be need not be onto, need not be one to one. Can be any type of functions.
Okay, so now
The only thing it should satisfy is a linear transformation.
so now let's say it maps from R3 to R100.
Yeah.
So dimension of kernel something, let's say.
Yeah.
Dimension of range is 100.
No, dimensional range is not 100. It is still 2. You should write down that function and see. That is the thing. Let me just write down this. Okay. So let's write down the function from R3 to R raised to 4, let's say. Yeah. Yeah, and the function is defined as f of x y c is basically equal to, let's say, 2x 3y 4c and let's say x plus y. Okay, I am just defining some function. Yeah. Is f a linear transformation?
Yes.
Yeah, you just write down, verify those conditions, you will find that it is a linear transformation. Yeah. Now, what is the kernel of f? Can you tell me the kernel of f? Only 0 0 0 vector, right? Because this thing has to be equal to 0 0 0. That means x has to be 0, y has to be 0, 0 has to be 0. Yeah. And so the kernel dimension of kernel is this is only the 0 vector.
So it's 0 0 0. Not
Yeah.
0 0 0 0. 3 zeros, not 4 zeros. Because V has to be in.
So this f of v, this is 4 zeros, no? F of v has to be in the r raised to 4.
Kernel of f is a element of this.
So this is this is R3. Yeah, this is subset of R3. You are right. Yeah, this is 3 zeros. Yeah. What is the dimension of kernel?
0.
Yeah. So remember that basis is a set of non-zero vectors. I mean, basis element cannot be a 0 vector because 0 vector is linearly dependent upon everything. Yeah, okay. I mean, yeah. So 0 cannot be part of your basis by definition. Yeah. So so when you have only the 0 vector as a vector space, the dimension is 0. Yeah, because you don't need any basis vectors. Means alpha times 0 is 0 itself. So, that is you do not need any basis. So, kernel of so dimension of kernel is going to be 0. What is the so this nullity equal to 0. What about the range? What is the range of f? What is the dimension of range of f?
It should be 3. Fourth one is linearly dependent expression.
So range by definition is a subset of W, is a subspace of W such that
It's exactly the definition we have in functions.
Is a set of set of elements in the W set, yeah, such that there is some input which maps to that W, yeah, and yeah, what is the range?
It's like range definition is same, only the input is vectors.
Yeah.
Also.
A comma B comma C comma A plus B.
Is the set of all vectors A, B, C, D, yeah, such that there exists x, y, c, yeah, such that A equal to 2x, B equal to 3y, C equal to 4z, and D equal to x plus y. I am just going by definitions. Yeah. Now, yeah, what is the dimension of range of f? Yeah. So, you can you need to prove that actually intuitively there are only 3 free parameters. Yeah, there is only x, y, c are the only 3 free parameters. Yeah, a, b, c, d are computed from x, y, c only. Yeah, so you can actually prove that the basis for range of f is there are only 3 elements in the basis. Yeah. So I can give you one explicit basis, for example. Yeah, so a basis for range of f, yeah, basis for range of f, basis for range of f, yeah. Let me just give you a basis which is 2, 0, 0, 1, yeah, and 0, 3, 0, 1, and 0, 0, 4, 0, and
That's it.
0.
All zero. That's it, which is conjugate. That's it, right? 3 bases. So
Yeah, so these 3 form a basis. Yeah, the claim is these 3 form a basis for range of f. You can actually span all elements of range of f using these 3 vectors.
So in the first one 2 0 0, it should be 2, no? Because it's x plus y the last one.
no, x, you're just taking x coordinate. Right? 2 is coefficient.
Yeah, so you need to prove, it's a very important homework actually. Yeah, to get comfortable you need to prove this. Yeah, so these 3 vectors form a basis for range of f. So first you need to prove that range of f is a subspace. I think that we already proved. Yeah, but these 3 vectors span range of f. Yeah, so the kernel, so the dimension of range or the rank, yeah, is going to be 3. Yeah, so 0 plus 3 equal to 3. Yeah, that is what the rank nullity theorem is saying. It seems to be working. Yeah. Okay. I think it is good that we got confused and we cleared this. Yeah, because there are fine details here. Okay, you have to be comfortable with this. Yeah, you have to work out some basis. How do you show that this is a basis for range of f? Not very easy. You have to work it out. Yeah, you have to show that every element of range of f can be written as a linear combination of this.
No, actually, I think it's easy. You can just say
yeah, just go back, think clearly about it, yeah, so that yeah, I don't want to discuss it right now. Yeah, I want everybody to go back and think about it. Okay, that's all for today, I guess. Yeah, yeah.